Hello, this is Arjank. Today I'm going to continue chapter 5 with example 18. In this example we are going to cover a frame with certain loads and we are going to calculate the displacement. So let's start. So in order to start this, let's start a new project, make it plane because we are in 2D plane. Let's call it chapter 5 example 18. Then the unity system is fine, admin, finish. In order to make it simple, let's make it front view, close the grid, and let's define point B as a 0, 0, point C as a 5, 0, and point D as the 25, 0. And let's call point A as 5 minus 12. Correct? So we have this frame. Let's click on this main page, add beam, and connect these nodes together. We are constructing the problem statement in your book. The next step is that we have to define, we have these. Let's go to the next tab, general. Let's define the material, create. In this material we have new material. In this material, so do you see the unit system is not matching, so we are going to go to unit system, input units, make it inch, then OK, then go to the create, make a new. Let's call the modulus of elasticity as 4500 KSI, and Poisson ratio is given to us because we are also considering the effect of the area in your deflection. So my Poisson ratio is 0.1, and when my Poisson ratio is 0.1, based on the calculation, shear modulus is 2045.45 KSI. Then add OK. So we define the material. The next step is that we have to define the cross section. So we have I and 2I. Let's go to the property, define. Let's assume it as a rectangle. So not rectangle, let's write general because we also need the area. So let's select a new material for us. For shear we have AY because the area is given to us 180, and for the moment IZ, let's call this according to problem statement 3500. Correct, and then add. This one is for I, and for 2I, let's call this 2 times 3500 means 7000. Then add, close. Then assign these to the horizontal members and the I to the vertical member. We define the cross section, define the properties, we assign them. The next step is that we have to define the supports. Go to the support tab, create, make a pin, add, make a roller, create, fixed spot, fx, fz, mx, my, mz, add, then assign pin to this node and roller to the right hand side, then close. So if we define the support, the next step we have to define the loads. So let's bring back the unit to the feet. Okay, load and details, go to load case details, add, load case number 1, add, close. Under this load case, let's define a couple of loads. We have add, nodal load, we have at the node B, we have 10 kips to the right and 10 kips to the down. So minus 10 here, add. The next step is that we have also the member load. The member load, that's minus 2.4 kip feet, and the length is 20 feet. Add, close. So assign this to node B and assign this to this member. Let's look at this. The size is good. We can see the values. Right click, labels, load values. OK. So if you see that it's exactly like our problem statement. Even if you want, you can see the dimensions. The next step is that we have to run this problem. Go to the analysis and print, add an analysis type, close. go to analyze, run analysis, save. Okay, the warning is because we haven't defined the complete moment of inertia and area, but the one that we put was necessary for this problem, and it's enough. Go to the post-processing. Okay, now we see the deflected shape. If you want to see it in an exaggerated way, go to this, make it displacement a little larger. So first, let's compare the reactions. Reaction should be fine. We have the reaction, we have the displacement, and all of them should be compared with the hand calculation. Vertical displacement at point B was calculated as minus 0.316 inch. So at point B, which is, let's see the label numbers, which is node number 1, we have 0.308 inch displacement. And for the also all of the displacements are comparable with the hand calculation. We can results, v values, note, we can see global y, annotate, close, and also in reactions also you can see the reactions for the bending moment diagram and shear force diagram also as well. It has been seen. So we had this bending moment diagram, shear force diagram, and this one is axial force diagram. Axial force diagram. So we see the axial force also, even this member has some axial force. So you can also adjust the scale for this. If you want to see the values, results, view values, beam results, shear and bending at the ends, annotate, close. And also you can print these views as illustrated before. Thank you so much. See you in the next one.